So I can start now. So the last time we talked about the Minimax theorem and tried to solve one example and 2 and 3 fingers more up. But the moment the size of the strategies is large, it becomes quite difficult to solve by trial and error kind of methods. So we need to develop better methods. And even it was a struggle for great mathematicians like von Neumann and Hermann Weyl. And it took a time when linear programming came out, and it's all thanks to again conversational advice by von Neumann to Danzig. That's how it happened. So our idea is not that we are going to go deep into linear programming. We only want to solve using the technique of linear programming. Okay, it is there are lots of side results and theorems within linear programming. You won't be able to get into it, then we will lose the game theory of it. Okay. So let us start with an example of a linear programming problem. Just take this simple example, maximize 3x1 plus 4x2 subject to x1 plus 5x2 is less than or equal to 7, 2x1 plus 4x2 is less than or equal to 9, 5x1 plus x2 is less than or equal to 12, x1, x2 non-negative. Okay? There are two ways of seeing this, one geometrically, another algebraically. Very important, almost any geometry is only intuition. It has to be finally backed up only by algebraic methods. Okay? Algebra is the foolproof method. And so, first step is what I want to call a dictionary. A dictionary. I write down this, convert all these inequalities into equalities. So, whatever is the difference between this number and this one, I call that as a new variable x3. So, x3 is 7 minus x1 minus 5x2. x4 is 9 minus 2x1 minus 4x2. Agree? x5 is 12 minus 5x1 minus x2. Okay? And call this as a new variable z. Z is 3x1 plus 4x2. So everything is basically a linear equation. Okay, everything is basically a linear equation. Can we think of some solution to this system of equations? We want also, because this is less than or equal to, x3 must also be non-negative, x4 must be non-negative, x5 must also be non-negative, x1, x2, everything should be non-negative. So we are looking for a non-negative solution to this system, this top system. Once you found any non-negative solution, you substitute it, that gives you the value of C, the value of the objective function. One of the simplest solution is, say, you can choose all the variables to the right and give them the value 0. Okay? You give them the value 0. As long as this right hand side everything is positive, you can use 0, 0, 0, then x3 will be 7, x4 will be 9, x5 will be 12. Okay? So, current solution is x1 is 0, x2 is 0, x3 is 7, x4 is 9, and x5 is 12. This is the current solution. And the value of the objective function is 0, because x1 is 0, x2 is also 0. Okay? This also I can write it in the matrix language. How do I write it? I write it with this as the matrix. A is 1, 2, 5. Please. Hello? Nema? Check. Perfect. Say, where about Undi? Right. See, I lost my flash drive yesterday and I was running amok, but she says she found it. That's good thing. Okay. 1, 2, 5. 5, 4, 1. Agree? I want to rewrite the same thing this way. 5, 4, 1. 1, 0, 0. 0, 1, 0. 0, 0, 1. Look at this is x1, x2, x3, x4, x5, which is same as saying equals 7 and 12. Do you follow me? I am rewriting the same inequalities as this equality, namely 1x1 plus 5x2 plus x3 is 7. Okay? 2x1, say 2x1 plus 4x2 plus x4 is 9. So, in a sense, these variables are associated with the columns. x1, x2, x3 are associated with the columns, and when you look at 1, 0, 0, 0, 1, 0, 0, 0, 1, they constitute a basis for the 3 tuples. Agree? They constitute a basis for the 3 tuples, and then you call this as a basic solution, a basic feasible solution. What is the basic feasible solution? Giving x3 is equal to 7, x4 is equal to 9, and x5 equals 12, and the other things at 0 is a basic feasible solution. You follow? Okay. Let me. Can I erase this whole item?
Yes, you can erase it.
Huh?
You can erase it.
Yeah, okay. Now I want you to use this textbook by Quatal, CHWATAL, on linear programming. For a long time I used to teach through different books. But I found Quata is the book which is closely tied to computer science, and also within the first 15 pages it is finishing the simplex method, whereas it takes centuries for the other people. They go through all kinds of nonsense. This person's thing is very nice. Okay. So this, when I write this one in this fashion, it is called dictionary. This fashion, we write it as a basic feasible solution. This is for purely matrix operations. This is for the real understanding. Understanding is through this one. Manipulation is through this one. First we have to understand, then we want to manipulate. So we should be confident what we are manipulating is what we understand. Okay? Now let's look at first step. Right now x1 is 0, x2 is 0. So all the variables to the right you put them as 0. Okay? Whatever comes on the left are the basic variables. These are the non-basic variables. Non-basic means they don't get a value non-zero. They are all 0 values. Basic means non-zero values. Okay? These are positive. Okay? Now I want to improve this function, the value of the objective function. Can I increase x1 from 0 to something positive? Okay? So suppose instead of x1 is equal to 0, suppose I put x1 equals 1. Say take x1 equals 1 and x2 equals 0, and then look for what happens to x3, x4 and x5. So I get x3 as 6, x4 as 8, x1 is 1, so this one is 7. x5 is 7. But these variables are not part of the objective function. Even though these numbers can change positive, etc., they are not really adding anything to the value of the objective function. Anything is added only when x1 and x2s are increased. Okay? So you need to increase either x1 or x2 or both. But better thing is, if you don't know how to change both of them, you change one at a time. So the whole principle is always, almost all algorithms, only thing you do, try to do one at a time. So I want to increase x1. So when I increase x1 to 1, the objective function's value is 3. But I could have increased to 2 too. Isn't it? I could have increased to 2. Can I increase it to 3?
For x5, it will become
If I put x3 is equal to x1 equals 3, this is okay. This is also okay because x3 will still be non-negative, x4 will be non-negative, but x5 will become negative. So you are allowed to increase only up to such that all these left-hand side things are non-negative. So in reality they should be positive. Okay? But when it is non-negative, let's see how far x1 can go. 12 over 5. So I rewrite this equation as follows. Now I am going to rewrite this equation as, I change this equation to take x5 to the other side and bring x1 to the left side. Whichever you want to improve, so try to bring it to this side and push the other one to the other side and rewrite it. For example, 5x1 equals 12 minus x5 minus x2. Agree? Which is the same as saying x1 equals 12 over 5 minus 1/5 x5 minus 1/5 x2. Okay? So, now try to, so what you have done is, these were so-called non-basic variables. This one was basic variable. Now you have swapped here. You want to make x1 basic, and when you put x5, it becomes non-basic. That means x5's value must be 0. Okay. And the way you work it out is write it this fashion. Okay. Write it this fashion. Then try to write down this equation x3 in terms of this equation. Okay. x3 is 7 minus, instead of x1 you can write down this 12 over 5 minus 1 over 5 x5 minus 1 over 5 x2 minus 5 x2, there is no problem. Okay. Which is plus 1/5 x5 plus 1/5 x2 minus 5 x2, which is minus x2. Yeah, maybe I can use it right now. So, I'm now going to write down these equations as x3 as 23 over 5 plus 4 over 5 x5, 24 over 5 x2. And then I have to do the same thing with x4. x4 is, I will do this here, 9 minus 2. Can you read for x1 for me? 12 over 5? Not clear. Loud?
1 by
Huh?
1 by
1 by 5?
x5
x5?
minus
Yeah.
1 by 5
x2. So that means 21 over 5 plus 2 by 5 x5 plus 2 by 5 x2. That is that's all? Correct. This is 9 minus 2x1 minus 4x2. I have to do another minus 4x2. Minus 18 over 5 x2. So x4 is 21 over 5 plus 2 over 5 x5 minus 18 over 5 x2. Then this one. This is equation which has been written the other way. x1 is 12 over 5 minus 1/5 x5 minus 1 over 5 x2. Now I have to write z also. 3x1 plus 4x2, which is 3 times. Instead of x1, I should write down 12 over 5 minus 1 over, what is that? 1 over 5 x5 minus 1 over 5 x2 plus 4x2. Agree? This is 4 5 minus 3 over 5 x5 let's simplify. 3 over 5. Okay, this is minus 350x2 plus 4x2. X2. That's what I get. Am I right?
Yes.
Please watch me. I am not really good at arithmetic. Okay. I know only multiplication better. Okay. So I am going to rewrite this as 36 over 5 minus 3 over 5 x5 plus 17 over 5 x2. When I write like this dictionary tells the current solution is put all the variables to the right as 0 and what you get is the current solution. So the current solution is, for example, x3 is 23 over 5, x4 is 21 over 5, x1 is 12 over 5, x2 is 0, and x5 is 0. So the value of z, the current value of z at the new solution, you put 0, 0, then you get z equals 36 over 5. The value of the objective function has improved from 0 to 36 over 5. Agree? Can it go further? Can we increase it further? Okay. Suppose you try to increase x5, then the value of z will only come down. If I increase x2, it will go up. So you look for one for which it will go up and try to increase that way. You get my point? So let's increase x2. When I say increase x2, in the entire procedure, always, when somebody goes up, someone else has to come down. Okay? You try to push this fellow as much as you can, so that somebody who was originally positive becomes 0. This is the key idea, nothing else. The key idea is to look for one variable, increase it, and look for the other variable, decreasing it, but don't increase too much so that something becomes negative. Ultimately, something should become just 0. Any one of the variable can become 0, and that variable is now, it is called the non-basic variable. Okay. So let us do that one. So when I increase x2, you look at this one. If I increase x2, x1 is coming down. If I increase x2, x4 is also coming down. If I increase x2, x3 is also coming down. Agree? Because right now the value, you cut x5 as 0, but you are only increasing x2. Okay? How far can it go? So it depends on comparing this constant with this one. Isn't it? Okay. Both are 5, 5. So if x2 is more than 23 over 24, if it is more than 23 over 24, this whole thing will become negative. Okay? So x3 has to be less than or equal to x3 must. Now the same way, I'm sorry, x2 must be less than or equal to 21 over 18. 21 over 18. Do you agree? Because if it's more than 21 over 18, this will become negative. Similarly, 12. x2 must also be less than or equal to 12. It should be less than or equal to this, less than or equal to this, less than or equal to this, which is the right choice. Huh? Because this is the least. Okay, this is the least. So the so-called Simplex algorithm in the table etc. says precisely the same thing. But here we understand what it is saying. Okay? Not pretend that we understand. So put x3 equals 23 over 24. Immediately, not x3, I'm sorry, x2. Put x2. x2 equals 23 over 24. Then this becomes 20 over 5 cancels, x3 becomes 0. Agree? So that means x2 becomes basic, x3 becomes non-basics. This implies x2 becomes basic, x3 becomes non-basic. So when we do this one, let's do this next calculation. At least once we have to grind it. Okay. So that means you bring it to this side and take it to this side. That's all. So I get 24 over 5x2 equals 23 over 5 plus 1 over 5x5 minus x3. Okay? So you need to write x2. Everything, these things should have coefficient 1. So x2 equals 23 over 24 plus 1 over 24x5 minus 5 over 24x3. Agree? x2 is there. So that is from this equation. Now this equation x4 equals, you can write down whatever it is. Okay, right now. I'm hoping to do less work if possible. So I'm now trying to write down one in the z. So let us calculate z here. Z is 36 over 5 minus 3 over 5 x5 plus instead of, which one was changing on this side? x2. So instead of x2 I should substitute this 23 over 24 plus 1 over 24 x5 minus 5 over 24 x3. So minus 3 over 5 plus 1 over 24 is plus some negative quantity times x5. Whatever is that number right now. And this one is minus 17 over 24 x3. Okay? So z is this one. So from this, what do I see? Maybe I can write down what the number is, it doesn't matter. If I increase x5, z value will come down. If I increase x3, z value will come down. So you cannot do these two things. They have to be 0. Okay? So once they are done, the optimal value therefore is z is, I don't know whether I wrote it correctly. There is a constant term which I have not added. So it is 17, okay, 1 minute. It is 36 over 5 plus 17 over 5 times 23 over 24. Okay? So, 24, 144, 23, okay, by 120 plus 120. Okay. I2 251 over 24. Okay. So I get 251 over 24 as the optimal value. And what are the basic values? x1, how much was x? Where have I written here?
Yes.
X1, x2 is
23
over 24.
Yeah.
Okay. So x2 is 23 over 24. X1 is 12 over 5. Is it 12 over 5? I'm not quite sure. Oh, here I have written here. No, but this one is when x2 is not basic. Now x2 is basic. So you need to substitute the value of x2 here to get this one. This is not a correct one. Okay? You need to write down what it is. You get my point? You get the basic point. Okay? I can grind it and solve it for. I should have chosen a problem where everything will come nicely, click. But I just chose a random point problem. That's the reason. Okay. So this is all the simplex algorithm, nothing more. Simplex algorithm is just trying to rewrite it this fashion. So the thing which it does is you need to do some of these things mechanically. In a sense, you learn how to mechanically do the same thing. That's the whole purpose of the next step of the simplex algorithm. Okay. So now I want to do the mechanical side of it. First, can you put the next slide? Okay, and push the next slide. Okay. For example, look at this matrix. Okay. A times 1, 1, 1 is 13, 17. So, if I want to solve this equation, x1 plus 4x2 plus 8x3 equals 13 and 2x1 plus 9x2 plus 6x3 is 17. One solution is say x1 equals x2 equals 1 is a solution. Now, I want to call this as, no, we have, is there one before that? This is the one? Later, maybe go, what's that? Yeah. No, I think maybe I missed something. Let me define it, okay? Let x equals b be a matrix equation. In unknown x. In unknown x. If x bar is a solution, we call it basic. We call a solution basic if the columns corresponding to non-zero values of x bar's coordinates are linearly independent. You follow me? Let me explain one more round. When you are given this equation, there are two ways of, here is this equation. This is the matrix A. A is 1, 4, 8, 2, 9, 6, x1, x2, x3 is 13, 17. You can write this equation this way as a matrix equation, or you can also write it as a vector equation with this x1 times 1, 2 plus x2 times 4, 9 plus x3 times 8, 6 equals 13, 17. So this vector is this linear combination of these three vectors. Both are same. Okay? Now we found one solution. 1, 1, 1. But these vectors 1, 2, 4, 9, 8, 6, are they linearly independent or dependent? They are linearly dependent. So I will also come to the definition of linear independence now. Okay? So let me start from the scratch. Let V be the vector space Rn. That means all n tuples, column n tuples. Think of them as column n tuples. V1, V2, Vn are linearly independent. I can put V1, V2, Vk are linearly independent if and only if summation alpha I vi, I equals 1 to k, is the null vector, implies alpha 1 equals alpha k equals 0. The only linear combination of these vectors which gives the null vector is the zero vector. Agreed? That is the definition of the linear independence. So what I want is a solution is called basic if the coefficients which are non-zero, the x's which are non-zero, the corresponding vectors must be linearly independent. So the 1, 1, 1 fails to satisfy this condition because 1, 2, this is positive, this is positive, this is positive, and 1, 2, 4, 9, 8, 6, they are linearly dependent. Okay? Fine. So the first theorem if Ax equals B has a solution x star, then it also has a basic solution. It also has a basic solution. What does it mean? You can, whatever you want to say, you can say. It doesn't matter. We can modify it.
There is a solution for said the columns are linearly independent.
Huh?
There is a solution so that the columns are linearly independent.
Correct. So, if I start with the solution x star, I can always find another solution. Okay, I can always suppose x star is some solution, and it will have certain coordinates non-zero, the other coordinate 0. Whatever coordinates are non-zero, the corresponding columns, if they are linearly independent, you stop. This x star itself is a basic solution. Agree? If x star without loss of generality is of the type its first coordinate times the first column of A plus second coordinate times the second column, eighth column, equals plus the rest are 0, 0 times ck plus 1 plus 0 times ck plus 3m equals B. Because suppose you are assuming A is an m by n matrix. And suppose all these are non-zero. All these are non-zero. So x star 1 is non-zero, x star 2 is non-zero, x star k is also non-zero. It can be negative or positive, but they are non-zero. In case these columns are independent, linearly independent, we stop. In case C1, C2, Ck are linearly independent, we stop. So what we have is itself a basic solution. Agree? What we have is a basic solution. Suppose they are not. Agree? Suppose they are not. What does it mean? That means I can find some coefficients alpha 1, alpha 2, alpha k such that the linear combination of them gives you the null vector. Well, some alpha is not 0. Do you follow me? The definition of linear dependence means if they are linearly dependent, what does it mean? It means, can I erase this? Maybe we close this one for a while. So we have alpha 1, C1. These are scalar, this is the vector, remember that. Alpha 2, C2 plus alpha k, Ck is the null vector, and one of the coefficients, alpha 1 or alpha 2 or alpha k, is not 0. If everything is 0, it's so good. Good. You already know. It is a non-trivial combination which gives you the null vector. Okay? So now we can rewrite the following. x1 star c1 plus xk star ck plus 0 ck plus 1 plus 0 cn is b. You can write this one as alpha 1 c1 alpha k ck plus 0 ck plus 1. You can write 0 cn is also equal to the 0 vector. Agree? Are you with me? Okay. Now, one of these x's is not 0. One of these x's is not 0. And one of these alphas is also not 0. Okay. One of these for I less than or equal to k, one of these alphas not 0 for I less than or equal to k.
All,
Well,
all the xi stars are non-zero.
huh?
All the xi
Yes,
stars
yes.
are non-zero.
Beautiful. Not one of these, all of these. That is crucial. In fact, it's critical. Thank you for wonderful critical observation. It's a very critical observation she made. So, what I can now do is x1 star plus or minus alpha 1 times c1 xk star plus or minus alpha k ck will be equal to b, because whether you do plus or minus, it's the same. Agree? So what is the thing which I can now do? I can there are several possibilities. One possibility is some one of these is positive, x1 star or xk star is positive, or they are all negative. Okay. Either some one of them is positive or they are all negative. Okay. So, in case it is they are all negative, you can choose you can change the sign of this and one of them will become positive. Okay? By changing the sign if you need, you can make it positive. So what you can do is pretend, for example, suppose x1 star without loss of generality is positive. Suppose. Okay? Then what you can do is x1 star minus some little epsilon times alpha 1 c1 plus x2 star c2 xk star minus epsilon times alpha k ck is also equal to b. Agree? It's also equal to b. But we are not adding anything special there. Okay? So what I do is I slowly increase epsilon. what can happen? If alpha 1 is positive, this will bring down. If alpha 1 is negative, then I make this as plus everything. Okay? Choose the right sign such that this is x1 star minus epsilon alpha 1 is coming down by increasing epsilon. At some stage, this will become 0. Okay? So for sure, one of the coefficients is going to become 0. Some other coefficients may also become 0. But for sure, one of the coefficients can be made 0. And this is also a solution. It's also a solution. So we have a new solution. A new solution. X bar such that in the first k coordinates, one of them is 0. So that means you are not using all the C's, you use not all the K, at least one less. So you come to, by induction, you can repeat the same argument, okay, till the starting thing itself is a basic solution. Are you with me? Is there some? You need to think. It's not a trivial thing. You need to think one more level. Okay. So, thus we have reduced the number of non-zero coordinates to k minus 1, at least to less than equal to k minus 1. Agree? Because some other coordinate can also become 0. But as long as when there are 0 coordinates, those are variables are not contributing. With the rest of the thing, you are representing B. And as long as they are linearly independent, we are done. Agree? So, you have to, at some stage, you have to end with a linearly independent set. If it is just 1, certainly it is linearly independent. As long as it's not 0, it won't be 0. Okay, that's it. So that is the proof of this theorem. So what does it say? It says every solution for a linear equation admits a basic solution. Okay. Can you press the next page? Now pull this down. Yeah. Okay. Yeah. Now look at the same problem with one more level of seriousness. Let C1, C2, Cn be the columns of an m by n matrix A, and let B not equal to 0 be a column m vector. Suppose we are looking for a linear combination of the columns where the x's are also non-negative. I am looking for a non-negative solution to a linear equation. It's something more difficult than just a solution. Just the solution depends on rank and dimension, etc. But this one is a little more geometric in its spirit. Okay. In general, such a solution may not exist for a given matrix and a vector B. In general, there may be a solution, but may not be a non-negative solution. See, there may be a solution that it may not be a non-negative solution. So, if there is such a non-negative solution, we call it a feasible solution to the linear equation. The word feasible is used to refer to non-negative solution. Are you with me? Okay. In matrix equation notation, you can write like this. Push the next page. See that. Okay. If x1 c1 plus xn cn admits a feasible solution, then it admits a basic feasible solution. What does it mean? It admits a solution where those coordinates which are positive, the corresponding columns are linearly independent. The proof technique is essentially what I wrote previously, the same trick, nothing special. In fact, it's easier than the previous case. Okay? It's the same thing. So can you push maybe the end of it? Okay. We can, the reason when I said epsilon I can increase, how far can it go is expressed in this next step. Okay? So the following theorem is essential for moving from one simplex table to another, and this is one of the basic theorems in the vector space. Suppose F1, F2, F1 is the basis for Rm, and phi and x is another vector which is some linear combination where phi1 is not 0, then you can toss F1 and replace it by x to be another linearly independent solution. Do you follow me? Okay, so what does it say? Let me write down. Say for example 1 0 0 0 1 0 0 0 1 is a basis for R3. Agree? Any vector is a linear combination of them. Now, suppose I take this vector, call this as V1, call this as V2, call this as V3. Then I write down a new vector V4 as, say, or V as 2 minus 5, 1. 2 minus 5, 1. Agree? No, I don't want to write it. I want to write, yeah, 2 minus 5, 1. You can choose. So that means V is a linear combination of 2 times V1 plus minus 5 times V2 plus 1 times V3. As long as a coefficient is not 0, so this coefficient, for example, is not 0, what theorem says is, I can, while V1, V2, V3 is a basis, I can toss V2 and put it in its place V. So V1, V3 is also a basis. This is the so-called change of basis theorem, which is very critical for the simplex algorithm. Okay, it's very critical for the simplex algorithm. Now let me okay. Now I am going to do the mechanics of the simplex algorithm. Okay? Just you appreciate the mechanics of the simplex algorithm, how it works. So I am going to take the same problem. Okay? What was our problem? Problem was maybe I choose some other problem, it may not. Yeah. So what was our problem? Let me see.
Maximize 3x1 plus 4x2.
Maximize
3x1 plus 4x2.
3x1 plus 4x2.
Subject to
Yeah.
x1 plus 5x2 less than or equal to 7.
x1 plus 5x2 is less than or equal to 7.
2x1 plus 4x2 less than or equal to 9.
9.
5x1 plus x2 less than or equal to 12.
5x1 plus
x2 less than or equal to 12.
and all the x1, x2 are it.
Yes.
Okay. So now I am going to write down in the matrix language. So write down on the top x1, x2, x3, x4, x5. So this is 1, 5, 1, 0, 0. On this side, we write down 7. So x1 plus 5x2 plus x3 is 7. Yeah, maybe you should take it down. Okay. Okay. Then the next one is 2, 4, 0, 1, 0, 9. And 5, 1, 0, 0, 1, 12. And this one you write it as z. This equation you write as z minus 3x1 minus 4x2 as 0. You follow me? You can write it like that. Here you put a z as a variable 0, 0, 0, 1 minus 3 minus 4 0, 0, 0, 0. So this represents what I am saying. Z minus 3x1 minus 4x2 is 0, 0 z plus 5x1 plus x2 minus plus x5 is 12, etc. It is the same thing written in this form. Okay? So our mechanical method is to look for these negative quantities. Look for the negative quantity. So which means this is, you can start from anywhere, it doesn't matter. It's all known that there is no real efficient procedure beyond this. So start here. So that means I am trying to, now you write down wherever you find this 1, 1, 1. This one is x3, this one is x4, this one is x5. These are called the basic variables. Okay? Now this is, see, the point is, this constitutes the basic variables for this particular table, for this table. Okay. Now, because these are all 0, 1, you don't write this particular. You can keep it, but this is not going to do anything. You can, even though this is for explanation purpose, you don't need it actually. Okay.
Your phone's offline, so I can't help you with that at the moment.
Okay. Whose one? It's not mine. Okay. So now what I did was, previously, I said, you take this ratio, 12 over 5, 9 over 2, 7 over 1. Choose the minimum. Okay? Which is 12 over 5. That happens here in this. So you put a circle around it, which is equivalent to saying x5 is going to leave the basis, x1 is going to enter the basis. Do you follow me? Please stop me, because after all you should know how to solve another problem. Okay? Now this says I am increasing the value of x1. I cannot increase beyond a certain level. And beyond that level is determined by this ratio, this over this, this over this, and this over this, only over positive coefficients here. Remember that, only over positive coefficients. Why positive coefficient I can explain later, but don't worry. Right now we are learning the mechanics of it. Okay? So now, this is the one which is going to now, x1 is going to enter the basis, x5 is going to leave the basis. Each time you keep only 3 of these vectors, 3 of these variables with basic variables. And something leaves, something enters. Here first we decide which one to enter by looking the last row. And which leaves is decided by this ratio test. It's called the ratio test. Okay? By the ratio test we decide. So now what is the next step? Next step is very mechanical. All you do is, you do row operation. You can add one row to another row. You can multiply a whole row by a number. You are allowed to do such things. But the only thing which you ultimately do is that this must become 1, this must become 0, this must become 0, this must become 0. Except this pivot entry, it's called a pivot entry. This must be 1, all the other things must be 0. Okay, let's do that. So it is going to be, instead of x5, I am going to now write down x1. 1/5, 0, 0, 1/5, 1/5. Okay? Then use this row, suitable multiple of this, and with this you add, then it must become, this must become 0. That means multiply this by 2 and subtract from this. So you get x4. I'm not writing this column. Forget about it, okay? It won't change. See, this will never change no matter what you do as an operation because all are 0. Okay? So this one, now this one is 2/5. 4 minus 2/5. How much? I not Please allow me to use my Tamil language, which is a great language for mathematics manipulation. Okay. This one is 4. This one is 0. This one is 1, 2/5, 2/5, 3/5. Please check my Please check my calculations. I multiply this by 2 and subtract 2/5. Zero. No, so this one is 0. 0, yeah?
Yes.
Yes. This one is 1. 1. This one is 2/5 minus 2/5. Minus 2/5. This one multiply this by 2, 9 minus 2, okay? That's what we had. And then the next one is, at least this one is easy. This is 1. So directly subtract 5 minus 0, 0, 1, 0, 0. 1/5 minus 1/5. This one is 12/5. 7 minus 12/5. Okay. And then last row, you multiply this by 3 and add to this one. 3/5 minus 4 plus 3/5 minus 17/5. 0, 0, 3, multiply this by 3, 3/5. 5. Okay, that is the current solution. Agree? So you can even check what is the solution. So when I take, for example, take the basic variables. Agree? Now x4 is 21/5, x1 is 12/5. This one was, what was this? This one was x3. x3 is 23/5. Those things don't contribute to, except for x1, the rest don't contribute to the objective function's value. Okay. Now this fellow enters x1, x3, x4, x5, b. Okay. Now this fellow enters. Again, do the same ratio test. This over this, this over this, this over this. We saw that this is the least. 23/24 is the least. That's what we remember also previously. Agree? Any doubt? Yes? Okay. So now you need to make this one by dividing the entire thing by 24/5. Agree? So let us do that. That means x2 enters the basis, x3 leaves the basis. x2, x1, x2, x3, x4, x5, 0, 1, unlimited error, 0, minus 4 24, 23, okay. So this is the pivot entry. You always circle this as the pivot entry and use suitable multiples of that to make this entire column other than that particular entry 0. Okay. So that is the mechanism. Whatever we did as a substitution of one variable in terms of other variable, all these things are finally this thing, nothing else. Okay. Now this next step is multiply this by 18 over 5 and subtract. So this gives you x4, 0, 0. This is 18 over 5 times 5 or 18 over 24. 18 over 5 times 5 or 18 over 24. Then this one becomes minus 18 over 34. This 0, this becomes, no, I don't know what happened. This one is 0, this is 0, this one is 18 minus 10. This one is 0, this is 1, this one is 18 over 5, which is minus 1 over 18. Multiply this by, just by 18 over 5, which is 18 over 5 minus 2 over 5 plus 1/5 times 18 over 5. Is it not? Please check, yeah. Because you need to multiply this whole row by 18 over 5 and subtract from this row. So I get this whole row by 18 over 5, which is 18 over 24, and then 18, this one is, this is 18 over 5 times 1 over 5, which is, yes, minus 2 over 5. Is it plus or minus?
Plus.
Plus?
Yes.
Yeah, minus 1.5. So therefore, I end up with minus 10 plus 10. Minus 8 25. And multiply this by 18 over 5, which is 23 over 18, and subtract from 21 over 5. I over 90. 263 over 90. Last one, x1. Multiply this by 1 over 5 and subtract from this 1, 0, 1 over 24 minus 1 over 24, 1 over 0, 1 over 5, which is 1 over 5. Multiply this by 1 over 5 and subtract 24 and 25. Okay. And then multiply this by 1 over 5. So this is 23 over 120 and subtract from this. And 24 correct, minus 265 over 120.
Plus 8 by 25.
Huh?
Plus 8 by 25.
Second
Second row, 4.
yeah.
Second row.
Oh.
Plus 8 by 25.
Plus?
Plus
Plus 8 by 25.
Plus 8 by 25. Okay. Okay.
Just a question. Previous. Just previous.
This one? What is the answer there?
Plus 8.
Plus 8.
Plus 8 by
And
25.
sir, also
Yes.
263 by 90 is not correct.
Huh?
263 by 90 is not correct.
265 by
263 by 90. The second row itself, last. Second row, last one.
this is not correct.
This should be minus 309 by 25.
There is no negative. There is something wrong. It can never be negative. Now, let's do this one, okay? And we have to satisfy ourselves mathematically. So, this one, I am multiplying this whole thing by
18 over 5.
18 over 5. So, it is this one you want to check, okay? Okay, 21 over 5, where did I write 21 over 5? 21 over 5 minus 18 over 5 times 23 over 5.
No, that's the mistake I did. It should be 23 over 24. You are right. I did the mistake.
23 over
24.
24. Over there.
Because we are seeing the new
last
x. New
name.
x.
Yeah.
We should compute it in the last one.
Yeah. Oh, 23 over 24, yes? So, 5, 24, 24, 2, 24, 48, 50. Isn't that? Just a minute. 21 over 5 minus 18 over 5 times 23 over 24. This is correct. So, 24, 24, 2, 24, 40, 50, 13, 54, 12, 41, cycle 90. 90 over 120. Yes? 90 over 120, but not this. Yes?
3 by 4.
Okay. This one is 3 by 4. And more than that, let's come to the last one. Is this correct? Hopefully. Hopefully it is correct. So that is the reason why we really need calculators. Beyond 3. Okay. Now imagine. See, this guy there's a famous theorem of Ramanujan. The theorem is concerned about how many possible partitions of a number are there. Suppose you have 8, 1 plus 7, 2 plus 3 plus blah blah. So every one of these partitions he is adding and counting the number of partitions. Okay. And then given any n, is there a formula by which you can write down the number of partitions? This was a challenge for Ramanujan and also a challenge for Hardy. They both were working very hard. Hardy, as a trained mathematician, formally trained mathematician, never believed that there could be any closed formula. Okay? But Ramanujan would not listen to him. But Hardy never tried to upset him because his thinking process is way deeper than Hardy's. Hardy's is a formally trained mathematician. The more formally you are trained, the less original you are going to be. The originality is something which has to come from outside your source. And then he wrote down a formula and he claimed it is correct. But somebody spent 2 months working out all the possible combinations. It's a huge number of something like 20 digits or so. And then it was accurate to just 1 digit. But suppose this number is, imagine, 2,000,001. His formula gave 2 million. That is the level of accuracy which he had. Ramanujan. I knew Ramanujan's, even though I don't know Ramanujan because he died long back, I knew Ramanujan's wife very well. She lived in my locality. So every 22nd of December, I used to go to their house She was a widow by 16 or 17. She was living and making a living with stitching clothes, etc. And they were family friends. She was a family friend. The same street, in one of those slum houses, she was living. We were living in one slum house, she was living in another slum house. So I used to go and prostrate 4 times before the main photo of Ramanujan. And then she used to cook some payas and things like that for me in those days. She lived till 99 or so. She lived a very long life. Okay. And then she used to have the collected works of Ramanujan. So I used to read this particular thing specifically. I will mention this to her, and it was a great soul. These are, I mean, people like Ramanujan or Bharati, they are very profound people. They make great difference to Indian maths. So now we multiply this by 17 over 5 and add to this. Okay? So this becomes 0. This becomes 0. This becomes 17 over 24. This becomes 0. So we minus 1 over 24 times 17 over 5. 150, and we need to multiply this by 17 over 5, 17 over 5, and add to this. 23 over 24 times 17 over 5 plus 36 over 5. 17, 55, 12, 34, 39, 120, 251 over 20. I don't know, we got similar number. I hope this is the number. So basically the principle is one is this. Okay. Basically this is the principle. And then what is the solution now? The solution is x1 must be 265 over 120 and x2 must be 23 over 22. Something like that. So this is the simplex algorithm. And incidentally, even though Danzig found the simplex algorithm, it was a profound rediscovery. It was Fourier who, a century back, already studied and gave the simplex algorithm. It was not recognized. It was not recognized that Fourier first found the simplex algorithm. But it was made more prominent by Danzig, even though he was not aware of that other one. But also the impact of Danzig is phenomenal because Fourier was only concerned as an algebraic equation and nothing more. It didn't kick him. We have a constant problem with pure mathematicians. Many pure mathematicians are very happy to prove the existence and forget about it. See, this is applied mathematicians who want to use it, they want a constructive proof. You just don't have constructive proof for many of them. And that is the reason why the modern computers and computer science have given a new thrust for respecting people who work in the fields of clay and other things to get the answer. So even now I never minded grinding this because the grinding is an integral part of learning also. Of you are sure that this is correct. That's the kind. Okay. So now once you know this, once you know how to solve like this, I am now going to write down one of our game problem, agree? And leave it with the simplex table. You need to solve it, okay? Can you put OPs not here? You can operate that. You know, huh? Oh. Okay, yeah. So yesterday's thing, we need to, yeah, we can operate. Okay, we know the yesterday's file, not this file. Yeah. Okay. Because it is a game of 1, 2, 3 business. Okay. Let me write down maybe 1, 2, 3. 1, 2, 1, 3, 2, 3, 1, 3, 2. So it is 1, 1, it is 1, 1, it is 2, is 1, 2. It is 3, 1, this is 2. This one is 3, 2 is 3. This one is 2 is 2. 1, 3. This is 1. This one is 3, 1 is 2, 3, 3, 2, 2, 3.
3, 2, 2, 1, 1.
Huh?
3, 2, 2, 1, 1.
Which one?
3, 2, 2, 1, 2, 1.
Oh, 3, 2,
2, 1, 1.
1. Okay, that's made. You don't need that now. Because, okay. No, I have to take more time. Okay. Now, I want you to write down this. Now, in game theory, you have one more simplification. You notice that the game value is positive. Agree? Value is positive. So, what we are trying to do is find minimum value V such that 1 Q1 plus 1 Q2 plus 2 Q3 plus 2 Q4 plus 3 Q5 is less than or equal to V. 2 Q1 plus 3 Q2 plus 1 Q3 plus 3 Q4 plus 2 Q5 is less than or equal to V. 3 Q1 plus 2 Q2 plus 2 Q3 1 Q4 plus 1 Q5 is less than or equal to V. Qi is non-negative, Qj is sum of Qj is 1. Do you follow me? That means choose any probability vector which guarantees something whose loss is no more than V, and I want this V as small as possible. I want this V as small as possible. But you do know that the V is going to be at least 1. You need to at least lose 1. So V you know is positive. V you know is positive. So we can divide by V and write down these as with one variable less. When I divide by V, we lose one variable. Agree? So I am going to rewrite it. So let us call Q1 over V as Y1, Q5 over V as Y5. Okay? So I get 1 Y1 plus 2 Y2 plus 2 Y3 plus 2 Y4 plus 3 Y5 is less than or equal to 1. 2 Y1 plus 3 Y2 plus 1 Y3 plus 3 Y4 plus 2y3 plus y4 plus y5 less than or equal to 1. And what do you know about y1, y2, y5? They are all non-negative. What do you know about the sum? What is the sum of all the y's?
1 by
Huh?
1 by
1 by v. Okay. So, you want to minimize v is the same thing as maximize 1 by v. Isn't it? If you want to minimize v, it's the same as maximize 1 by v. But 1 by v is nothing other than y1 plus y5. Okay? So you are maximizing. Do you follow me? Please stop me if you don't follow. So that is the linear programming we have. Do you follow? See, if I divide everything by v on the right hand side, then you get a number. If I call q1 by v, q2 by v, or q5 by v as y1, y5, since q1 plus q2 plus q5 is 1, q1 by v plus q5 by v is 1 by v. And if you want to minimize v, it is the same as maximizing 1 by v. But 1 by v is the sum of y's. So you are maximizing sum of y's subject to these constraints in y, which are non-negative and on the right hand side 1, 1, 1. This is a linear programming problem. Okay? So once you get the solution, you have two we call in Tamil, what I call a rendu manga. That means if I throw a stone, not only you get one mango, but also you get another mango. And what is the other mango? The other mango is what is the optimal solution for the other player. It comes from the same table. Let us, in this, whatever is our, what is the next thing called?
2000.
Huh? No. After 11:30. A tutorial. In the tutorial, we can work on this problem. Okay? And I have one more problem, two more problems for the tutorial. So this way tutorial is the right way to grind it. See, when we were students in Presidency College for statistics, morning time it's all lectures. In the afternoon it's all statistical tutorial, which means if they give you some problem, a statistical problem, you need to do basically sum of squares. That's all the work in factorial design or analysis of variance, two-way classification, anything. Okay. So we used to share the work. Then you find all the total and then find the squares. I find individual squares and sum and give you the wind ups and things. So, but it helped us to really appreciate the statistical problems. Okay. So here also you will appreciate it better. Okay. I think I will stop now. This is the time, isn't it? Or I have some more time to borrow. No. No, I really wanted to tell you, if I had 5 more minutes or 10 more minutes, I wanted to tell you about Ramanujan's squaring a circle problem, which I used to talk in schools. Anyway, later. Yeah.